explaining that what exactly is being done here, what is it being portrayed, or what is it that it is being conveyed, the easiest way to explain is simply by saying that with keeping all else constant, okay, you take only one term at a time. For instance, you take only this term, that is the beta naught. When you take beta naught, you consider everything else to be constant, or in this case zero. In this case it will be zero.
Prithvi, Vijay here.
Yeah, yeah,
Prithvi, before starting, right, I know this is a more technical kind of a thing you're giving legation, but before, right, see, to me, right, as a layman, right, when you say linear regression models, right, so where all
yeah,
can you use
yeah.
this? Right? For example, okay, you can use, like, for example, you're talking about one of the real estate kind of a thing where you can the housing price. So, but in real world, right, if I ask you, right, where
In
all
the
can
real world, in the real world scenario, let's say you are trying to predict any quantity which is measured in terms of continuous values. For instance, sales, okay, sales across various stores, or you can say your profit, right? So these are what? These are continuous values. So wherever there is a scope of predicting a quantity which has a continuous attribute, okay, in those cases or in those circumstances, one may, again I'm using the term, one may use a linear regression as a modeling technique. Okay, so wherever you fit this definition of a continuous random variable, I'm again using the term random variable because unless the event has occurred, you do not know about its outcome, hence the word random. So wherever there is a scope of measured quantity which is continuous in nature, okay, for instance somebody's height, somebody's weight, sales, or say rainfall, all of these can be denoted by, or all of these can be represented by continuous values. Again, as opposed to let's say your you have discrete values as well. In many cases, I am not able to recollect, there are, in many examples you have discrete value. So for instance, number of cars owned in a particular neighborhood, okay, so obviously it will not be a 1.5 car, 2 or 2 point something. It will always be either 1, 2, 3, and 4, right? So in this case, you will not use a linear regression. Why? Because your quantity of interest or your variable of interest is not continuous in nature. But wherever you encounter any variable, linear regression, you might not use it as your final model, but you can very well start with, or you can perform your analysis with the hope that linear regression model should be sufficient. Okay, because many a time we come across lots of variables where the relationship of the x's, that is the predictors, with the response is not linear in nature. In that case, we use a higher degree polynomial. Okay, so we need not restrict ourselves to linear regression. It might become a polynomial regression as well. So in such circumstances, we use a linear regression model. Okay.
Okay, so I
So
have seen. See, see, I'm
yeah,
talking about the industry side, Prithvi, right? See,
yeah,
I have a machine, I have an asset, right? For example,
right,
my asset is
right,
giving some machine data to me. For example, that
right.
machine data,
Okay,
I'm saying that, right? Okay, I have to have prediction, right? That my machine will fail in the next 1 month, right? Because
right.
the over temperature of the machine, right? The temperature is getting increased, and I am recording it. So, can I use
Okay.
linear regression there?
No, in this case, no, because you look at your problem statement. It says your machine is going to fail in the next 1 month. So you want to predict when
Mhm.
exactly is it going to predict? Is it's going to fail? Okay. So in this case, you will not be using linear regression. In fact, what you just spoke about comes under something called as survival analysis.
Okay,
There is
fine,
something
fine.
called as Cox hazards
Okay.
proportion.
Okay, okay.
Okay.
Yeah, carry on,
That's
carry on. I am fine.
yeah.
You carry on.
Okay. All right. So here, as we are discussing, the
And to the
expression.
team, right?
Yeah.
See, Ms. Prithvi, right? I'm also asking to the team, right? If you have any specific
Yeah.
questions, right? Please stop and ask Prithvi, right? There is no hard and fast rule. We have to talk at the end of the session, right? You are
Yeah.
open to talk at any point of time. You can, because I'm asking, right, because I have this doubt. I'm asking in front and between the session. So anyone have any specific questions, you can stop Prithvi and ask me. No problem at all.
Okay. So, okay. All right. So we can continue. So again, going back to this expression. So how do we define, or how do we express this to somebody if you're trying to interpret this particular equation? So we say that always keeping all else constant, when we look at one term in isolation, in this case, this term that is beta naught, which is independent of any x. So you can assume that all of these x's are zero. In this particular case, all of them are zero. So y hat, or in this case, the response is simply an average value of all the values of y. So imagine you have 10 or 100 rows, okay, 100 data points. So beta naught would simply, in that case, would be 100. I mean, some of them, some, all of them divided by 100. That's
Hello.
about it. Yeah. Hello.
Yeah, actually, I have seen the session was machine learning, right? So I
Yes,
just
you're
wanted
right.
to relate with that, how it is going to relate with machine learning and doing the
Okay.
things with
So,
respect to machine. Because
so
Vijay asked about the machine, but you said that it's
correct.
not going to. Yeah, please. Just
Machine
tell me
learning.
one use case in case we have some use case that would be great. Mm.
I think we had have a session in the last week. I guess we had a session where we had demonstrated this using Python, right? And if you're
Oh,
referring to machine learning as, okay, what is your idea about machine learning? Because what I understand, it is simply a fancy word for machine, sorry, for statistical learning. Okay, so you learn from data. You have historical data, you fit a model, and you try to predict. That is about it. But what exactly is your notion of machine learning, if I may ask?
machine learning is whatever data they are going to transmit, right? In case of there is a
Okay,
sensor is transmitting some data.
correct.
So and how we can manipulate those data, those things, that is what machine learning is there.
That is your understanding, but it is not
Right.
exactly what machine learning is. Machine
Right.
learning, simply stated, is learning from data. Okay, so let's take your example of sensor data. Fine. So imagine, now this is for everybody's this one benefit. Imagine you have sensors for every say you have air conditioning, heating. At least in India, I don't know about heating systems. I don't know. I don't think they have centralized heating. But imagine you have such sensors, all right? So something to control your voltage. I mean, you have various sensors in your house, imagine. Okay,
Mm-hmm.
so now what exactly are those sensors providing you with? They're providing with continuous reading, right? There is always, at every instant of time, you have some entry or some data which is being fed. Okay, so at once when you see that some malfunctioning has occurred, before that malfunction, some of the sensor, or the respective sensor, whichever is it, which is malfunctioning, whichever device is about to malfunction, or yeah, is giving some warning, will show some anomalous behavior, meaning the value or the sensor entries would be different, would be much different from what it usually is, right? So which means you are able to detect, okay, so you are able to detect that there is a problem at this particular device or with this particular device, and accordingly you will act. But
Great.
then what
Actually,
you, yeah,
yeah,
but in
yeah,
this
I
case,
understand. This is what
but
you are saying. That in the linear regression model, you are
no,
getting continuous
no,
data, and in that case, if something predict based on the continuous data, you are predicting the formula. Okay, this is going to calculate if
no,
there is some
no, no, no,
problem.
no, no.
Okay,
Actually,
please.
there's a
Sorry.
slight confusion here. I did not say you obtain continuous data. I said the data, the attribute itself is continuous in nature. By that I mean it is, okay, you understand, in mathematical terms, it's a real number. Okay, it's a continuous real number. Now you understand the value can have any number, sorry, the variable can have any number in the real number domain. You understand, capital R, real
Just
number,
consider you just consider temperature thing. Temperature has some range and it's sending some data with respect to temperature, right? Mm.
right? So imagine, okay, so there is a sensor which records it does not record the temperature, rather it says whether temperature is ambient, it is the perfect temperature for air conditioning or not. Okay, so that is the sensor data which is being fed, and it is stored in some system. Okay, so at once if your air conditioning is beginning to malfunction or it's not working properly, you get an alert. Okay, but in this case when you get an alert, you act. But here, where is the predictive nature? There is no predictive nature. But imagine if you are able to get this kind of data, which is, let's say, a month old, maybe 2 months, so on and so forth, maybe a year old data, you consolidate all of it, and obviously you must have faced some malfunction in the past. So all those data points wherever the malfunction has occurred are also present. You get it what I'm saying? Those malfunctioning data
Yeah, I
points are
understand.
also there.
So,
Yeah.
just wanted to understand the whatever malfunction you are getting with
Yeah.
by
Yeah.
applying this linear regression model, right?
No, in this linear regression domain, or within the purview of linear regression, this problem which I am discussing with you will not be covered. This is more of classification, that whether
Like I
a
think, Prithvi,
particular,
let me
yeah,
explain that, right? Nishant, see, Nishant,
yeah,
in the models, right, what you are talking about the machine data, what you are referring it is like it comes at a later point of time, because there are a lot of other models in this particular machine data, because every model is different from the other models. So what you're talking about, the IoT data, what is the machine data or Internet of Things data, right? It has a different way of modeling. So this is the kind, right, what we have discussed is in the entire machine learning, we want to go step by step process. Like in the step by step
So
process.
I wanted so I wanted to understand this linear regression model, how it is affecting the machine learning. Like, I just wanted to map with this linear. Can you give me one use case where
No,
this
no, no,
linear
see,
regression model is
Nishan. Linear
right?
regression model, to be very clear, right, as Prithvi is saying, that doesn't affect the machine learning data. So bottom line, right, this model doesn't link to your machine learning or whatever what you're talking about is. So that is a different model we are talking about. It will come at a later point of time.
Sure.
Okay.
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 So
I think there is a slight confusion. There is slight confusion. Let me just clarify. When you refer to machine learning, are you understand, or is your understanding is about data which is being fed from machines, from devices? Is that what you understand about machine learning, or is that what you refer to as machine learning?
So machine learning is kind of that what your machine is getting connected with some
No,
sensor
no,
and
no, no, no,
those
no,
is
no, no, no. That is not machine learning. That what see, do not take the word literally. When I say machine learning, it does not mean that you only get data from machines. Let's say you get logs or you get sensor data. That is not the only data, or that is not the data which comprises machine learning only. That is not any data. Okay, any data, any system which can provide you with data, any system which throws out data on which you can perform analysis by using these statistical learning algorithms. Okay, that process of learning from data, I'm again repeating myself, the process of learning from data is called machine learning. So please do not be confused about machines throwing out data and then using statistical
so
inference.
you
No,
mean to say any day if you have any data that is what you're learning.
any data from
Any data, whether it is
yeah.
just stored in the machine, that is the thing. It's not.
No, 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 no. Again, please don't bring machine
no, no,
into it.
Nishan, you're getting fun. So like your Twitter data, right? Your stock data or any data, what the Prithvi is referring, right?
Right,
Any data.
right. I understand. Please go ahead.
Okay.
Yeah, it could be any data. All right. Okay. Okay. So the next thing is how do you express the target with respect to these individual variables or these individual predictors? Again, keeping that the going with the same example, keeping all else constant. When I say all else constant means you have to ignore beta naught, beta 2 through beta p. We'll ignore all of these. And then you say a unit change in x1. That is, x1 increases by 1 unit. Okay, unit change, or it decreases by 1 unit. It says unit change. It does not say unit increase. Unit change. It could become x1 plus 1 or x1 minus 1, as the case may be. So how much of that is going to affect the response? It is going to affect by simply this amount, right? Beta 1 times that unit change. So the beta 1 is actually the effect of this x1 on the response. Okay, this is how you define a linear regression. This is how you express a linear regression. So for every predictor, you will have to say for all other factors held at constant, a unit change in that particular predictor results in a that respective, in this case beta 2 times change in the response. Okay, so this is how you uh, express a linear regression equation. So it's mentioned here in the text. You see, all other x is held constant. Okay. Now I think this would be slightly clearer for, or in this scenario we have a response which is y, and there are only two predictors, that is x2 and x1. So this is a three-dimensional problem. Okay, so our data exists in three dimensions: the y dimension, x1 dimension, x2.
Prithvi,
Yeah,
can you explain what is the least square fit first?
yes, I am coming to that.
Okay.
So let me first explain the diagram and then I'll come back to the least square fit. Okay. So in this scenario, imagine this entire expression is simply reduced to y subscript I equals beta naught plus beta 1 x1 plus beta 2 x2 plus the error or the epsilon. Okay, so there are only 1, 2, 3 and 4. There are just 4 terms. Okay, in this particular scenario. So now, what exactly is happening here? Trying to, when we say regression line, that is only when there are two dimensions. There is simply y and x. Imagine there is only two dimensions. There are only two dimensions, y and x. So in that case, your prediction would be a regression line. However, in our case, it's a three-dimensional problem. That is y, x1 and x2. Hence, the regression is going to be a plane. It's a plane. You see this? The shaded plane. This is the regression plane. So now coming to what exactly is this MSE, or this is a least squares. What is least squares fit? It means you take all your data points. Okay, you take all your data points, that is x1 and x2. These, imagine these are two variables, say x1 and y2, x2 are two variables, and the data consists around 1000 points. All right, so you'll have 1000 entries of x1, 1000 entries of x2, and 1000 entries of y. So you just have three variables in your data. So now how do you arrive at the best plane, this best plane, which will be the closest estimate of your function? What is the function here? Y1 equals beta naught plus beta 1 x1 plus beta 2 x2 plus epsilon. So this is your function. So in an ideal world, we should be able to determine the exact values for beta 1, beta naught, beta 1 and beta 2. However, since that is not a possibility, hence we try to be as close to reality by saying we try to estimate, or the best estimate of beta naught, beta 1, beta 2. Okay, now how do we arrive at that estimate? Now that is where we need to understand this least squares fit. So imagine we have multiple infinite numbers of planes can be fit here. You know, why only choose this plane? We can have n number of planes, but not all the planes will have this property. What is this property here? It is called the least square distance. You see, what is y1? Y1 is the actual value in the data which is present, that is here, which is actually present in the data. What is y1 hat? Y1 hat is the predicted value. Again, I spoke about those 1000 data points. That is 1000 data points of y, x1 and x2. From that data, when you fit it in the model, you get a y hat, which we had demonstrated in the example in the last session. That is y hat, which is a predicted value of y. So that y hat and the actual value will have some difference. It will always have some difference, correct? Why? Because of this. There is an irreducible error. This is called the irreducible error. So the idea is to bring them as close to each other as possible. Meaning, ideally, this difference should be zero, which is ideally, but it is never going to be a possibility or a reality. Hence, we try to bring them as close as possible. Meaning, the distance, or in this case the square distance, should be minimized. So let's say if this is a function, this is going to be a function on which we'll be using a minimization. So now does everybody know about partial differentiation? In that case, if somebody understands partial differentiation, it will be very easy to follow what I'm saying now. So imagine the error is denoted by this, right? So what are we trying to achieve? We're trying to minimize this. So how do you minimize it? Minimize any particular expression is simply differentiate it with respect to the variables. What are those variables? X2, x1. So this is going to be a partial differentiation with respect to x2 with respect to x1 equated to 0 from our plus 2 level math. So when you equal it to 0, you either get a minima or a maxima, as the case may be. In our case, it's a minima. Okay. Is it too complex, or are people able to follow? I mean, please let me know so that I can try to make it simpler.
I think right, to be really, it's becoming like it's too technical, right? I think right, we can just like we'll continue with the next thing, right? So just maybe high level, right? Maybe we can take an example and we can discuss about that.
Okay, I'll try to prepare a slide with do the simpler example. But then the idea is to you see these red dots. These red dots are the actual points. Okay, these are the actual points in space. Okay, so the idea is to fit a plane for which the square distance. You see, this is the distance. You see this line. This is the distance, but squared it. This distance is, in Euclidean distance you have, let's say, x1, y1. In this case, let's say it will be defined by 3, x1, x2, and y. The actual value of x1, x2, and y, that is here, and the predicted value. So the Euclidean distance squared. Only that plane will be chosen where the square distance for each and every point. The square distance for each and every point is the minimum, okay, is the least. So that particular plane is your function. In this case, this function. In that
so your square is the predicted one, right?
No. It is not the predicted. I'm talking about the error. Okay, the square distance.
I understand the square. What I got it.
Yeah.
You want to minimize this the dot which you are seeing, the actual one. You want to place it on the square.
On this plane. On this plane.
Yeah. And this plane represent what this plane represents. This plane represents the predicted data, and you want to see the actual data. Predicted data.
You got it.
You want to minimize minus y difference is minimum, then it is okay. Right?
Yes, you got it. So again, as I just told you some time back, the idea is to make the best guess or the best estimate. So this is the population line. So again, don't go by the word population. Population here represents the ideal line, or in this case, the ideal plane that defines all of these points together. What is that ideal plane? It is this, which we do not know, which we can never know. What we can know is the closest thing which is to this ideal plane. So this is what this particular expression that you see, this is what we tend to achieve by using the minimization of this function. And again another
so
technical.
What I understand, I understand in the layman side, y is the output, and x1, x2 is maybe the number of factors which is affecting y. Right?
Correct.
And
yes.
And by calculation, you want to just match with the predicted one, the actual one with the y, with different parameters. X1, x2, you can say these are the which is active value.
You end up with this. Now imagine if you get new data, okay, and you are saying that this plane is good enough to explain for the new data, you would not know what these points are, meaning what these y's are, you would not know.
Right.
So you simply fit this new plane and you get most probable values of y for the new data.
You will predict and you will see what is the actual value is coming.
you will see only when that event takes place, right?
Hmm.
Until that event takes place, you will not know. You can only hope and pray that yes, you have done something close to that event. So you should always, yeah,
Not put
exactly. So you will
prediction.
not check the results.
Whether
Yeah,
whether the actual things is happening 1 year later or something,
yeah,
you are just whatever
yes,
data you have collected, you are predicting for the future. It's kind of business analysis
exactly.
you
It
are.
is not kind of. It is absolutely that.
Yeah,
The
and
idea
that
is,
is what based
yeah,
on the 2 years data you are predicting it's going to be in next year or
yes, yes,
something like that, and
yes,
whether
yes,
you want to put money in this business or not, or I don't know.
yes, yes.
It's just a
Yeah, yeah.
use
This
case
is a good enough. And
I
if
can
you can
give.
understand it intuitively, it is good enough. You understood, right? What I'm trying to say.
Right, right.
Yeah, yeah. That's about it.
Got it.
Okay. All right. So, okay. So I will not get into the semantics here. So all you need to understand is make the best guess about these parameters, or in this case, you call them coefficients. Okay. These are regression coefficients. What are
Uh,
these? Yeah.
yeah, Prithvi, right. You have another only 5 minutes of this session, right? Because it will close in another 5 minutes. So how many?
Yeah. So now people can ask, if somebody want to ask question, because these are all technical terms. Like you said,
Right.
no, it will be better if I explain them simply. So
Yeah, yeah,
now I think we can have some Q and A's if people are
yeah.
somebody wants to
Absolutely. I
ask.
think that makes
Yeah.
sense, right? Because everything is a little bit theoretical, right? So people can go through that
Yeah.
theoretical.
Yeah.
Like if anyone has having like on a linear regression, right? People can ask questions,
Yeah.
and then maybe
Yeah.
right. Otherwise, we'll continue with the next class.
Yeah. And the next one would be no. It will be no longer a linear regression. It will be classification.
Yeah, absolutely. I know people understand that, right? Because
Okay.
see, overall,
Yeah.
what we are trying to give to the sessions, right? To give you a
Yeah.
bit flavor of what is what, right? So that people can go back and then try to dig into that, like whether they can apply into the machines,
Yeah.
which can be IoT
Exactly.
data or any can be any big data or whatever data, right? So that's
Yes.
what
That's
the
correct.
ideal understanding of. So next week, right, you can just talk about the classification and so on
Yeah.
and so forth on that.
Yeah. Yeah. So yeah. So anybody has any questions, you may ask.
So how many more classes you think, right, Prudvi? Like one is
I guess
classification.
around four classes would be sufficient.
Okay, so you're talking about the
I,
classification.
Yeah. So in classification, you have multiple types of classification algorithms. You have
Oh,
logistic regression. You have uh, tree-based decision trees. Then you have ensemble classifiers. You also have ensemble regression, but then that will be too technical. So I'll just limit myself to ensemble classifiers. And then you have unsupervised learning. That's where you come across these clustering techniques. That is where
okay.
you don't have any why as such. Nothing is given to you. It's simply provided with data, and you are asked to just find something out of it, or create or get some patterns out of it, if possible.
Okay,
so
good.
I think if there is no question related, you can complete this slide. If
Okay, so there are only technical terms actually.
Yeah.
What exactly are the measures of fit?
just in the
Yeah,
short, you can just in short, just explain the slides, whatever you are.
No,
Just
because
complete
right,
this
we are
slides.
getting
okay,
lot of time, right? I know, right? Basically, what we can
yeah,
do is we can put it on the, see, I have the PPT, right? I can share it according to that, right? And then people can go through that and then maybe ask some questions on that also.
yeah.
Okay.
Because see, this particular slide, it will be very very tedious to explain in say 5 minutes time. Okay, because I cannot simply run over this slide. This contains a meat of all the things that we've discussed. Okay, this particular slide. But
No,
then this is
I
a
understand.
heavily there is,
Yeah, so that's
yeah,
why we can just catch it up. So see
yeah,
what overall suggestion I think, right? See, theoretical you can
yeah,
get anywhere. See, overall what I try to understand, what I try to give it to the team, right? It's more of a practical
mm,
approach, more on the system, or more giving, like for example, last week I know Prithvi has given an excellent session how we can go and the Python. See, that kind of
Yeah.
questions is good to us, right? Sitting here, right? Because these all things you can get it somewhere, like whatever you want to do. But overall, like for
Right.
example, it can be applicable to some other things. So definitely it will help that.
Okay. Okay. So okay. So let's have it this way. Instead of having slides, why not I simply write codes and show the outputs
No,
and
no,
then
no, no,
explain.
no,
I think.
no, 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 not like that, right, brother? Don't take me wrong. See, what I'm saying,
Oh.
right? See, first of
Okay.
all, these slides are important because you should know what is what.
Okay.
So basically, right, today, if you ask, you don't know anything. Like my impression in this lesson, one class you can just
Yeah.
like first half an hour, 35 minutes. You tell the explanation. Today is excellent. You have given us an excellent linear regression and everything, right? So maybe we'll not
Okay.
go too technical, but you can give the entire high level information like what is what, and what is like next time also. So the
Okay.
next session,
Okay. I'll try to put illustrations, diagrams. I think that will be easier to follow. But again, I would request people. I mean, whosoever is watching this, and can you please open this website, this particular website? It okay. Can you check the? Can you see my this one URL? Can you see this URL?
no, we cannot see it.
Okay. Let me just put it. Okay. Wait. Okay, how do I check the screen?
Now, how do I?
You can put on like our group also.
Yeah. How do I
Hmm?
put a message? How do I put a message here?
No, you can.
Chat message.
No, in the chart window only you can put to
Yeah,
everyone.
yeah, chat window. Yeah, chat window. How do I chat? Okay, chat.
You just click on
Yeah,
window
yeah.
chat.
Okay, okay. I was nine. Oh, that was. Can you see this?
Yeah,
Sorry.
yeah.
Wait, no. So I misspelled that.
Sets.
No. Say SETOSA dot. Not those one.
Okay.
Click on that.
You can write it out right here. You can in the PPT. You can put it there. No problem.
Mhm.
Explicitly click on that. Explain.
I can see.
Yeah.